about nomenclature anyway, so we lost that first 5 minutes. Oh, mother of God. Oh, crap, I was recording it.
Again.
Silly
They're not
technology.
on my screen, so I can't see where to erase them. Okay. Okay.
And ask for the IUPAC name.
I'll cheat a little bit.
Which number was that?
This
6
is
from the nomenclature.
6. Nomenclature. Oh, mother of God.
I feel slightly better then. Because it uses the N in it. I didn't really.
Do you know what the answer is?
Yes, today.
Oh, good.
Usually
Okay, now I don't
they
feel
just-
so bad about it. So, good question as far as nomenclature goes, because it's a nice, hardcore, advanced one, making me feel stupid, so that's always good. Is this one that is going to be appropriate for the amine chapter?
Benzyl.
We don't have an amine. You're seeing the benzene ring, okay, which is another functional group, but there's something else more important going on with this.
Carbonyl.
We've brought a carbonyl near the nitrogen. That functional group is an amide. So the naming of this one is going to come back to the amide as your functional group. Okay? Kind of similar as far as thought processes go for naming your amide as you would for an ester. So in the ester, we name kind of the carboxylic acid portion of it. So when we're looking at the amide, where's our carboxylic acid portion? It's definitely going to include the nitrogen, the carbonyl, and that CH3. Okay? So if that was just an OH instead of NH, we could name this.
As an alcohol?
It would be a carboxylic acid. Okay, so if we just look within that purple section, we made that nitrogen and oxygen, we'd be looking at a carboxylic acid. Okay, the name we could come up with there might be acetic acid. Okay, since it's not an OH, we could come up with a couple options. We could go with acet, but now instead of acetic acid, it's what functional group? We could go with an acetamide. Okay, the problem that I would address with that is what is acet? That's a common derivative, okay? And the answer didn't have acet in it, right? Okay, so the acet is your common nomenclature system. So what would your IUPAC naming go by? No, let's jump into the answer, but that might give it away for you. Your common name, when you go through to name things, you go with the longest carbon chain. What is our longest carbon chain in that functional group? 2 carbons. Okay. We don't want to look at the benzene group because that's not part of our functional group. Our functional group is the amide right now, which is that nitrogen next to the carbonyl. Okay. And when we go through to name both our carboxylic acids and our amides, we're concerned about what's attached to our carbonyl. We don't care about the other direction.
So this would be a pair.
Okay. We'll get to that piece in a little bit, but that is a substituent on this main chain. So what we're trying to do is get the main chain addressed first. I know. So we've got 2 carbons, so we've got an F. Okay, what functional group were we looking at? An amide, so we could call this. Okay, ethyl means it's a substituent. It's not a substituent on the amide. It's part of the main chain. We could try ethamide. That definitely sounds a little bit weird. One of the things that we're going to tweak in with that is what types of bonds are there within the carbon chain.
Single bonds?
They're all single bonds, so it's not ethamide. We need to specify that they're all single bonds. Ethanamide specifying that hybridization. Please feel free to correct me if I stray from that answer. Okay? So we've now named that main chain, if we will. Okay? The next issue is that we haven't finished everything. We need to name the rest of that piece. We have a substituent attached to our main chain. Okay, where is that substituent located?
On the nitrogen.
On the nitrogen. How do we specify that it's attached to the nitrogen? So we'll need to see in our name an N specifying where the substituent is located on our ethanamide. Okay? So now how do we name that substituent?
Bromobenzene.
Okay, bromobenzene means it's not attached to anything else.
Phenyl.
So we need a phenyl to account for that ring. Okay, what else is on there? There's a bromo. Now where's the bromo located? So we could try the para position. I don't think we run with P in that, right? The reason why we wouldn't run with P is that we're now doubling up on our letter units. We've already specified an N, so we want to shift into that number system if we can. So where is that bromo located?
Third position.
So remember when we number our substituents, we always number where it attaches to our main chain. So that carbon is by definition number 1. We number around 2, 3, 4. We should be at 4 bromo phenyl ethanamide. Okay. If we want to make sure that we ensure where everything is located, you might also see parentheses dropped around that. They show those two.
Would you not use the P, O, and M because
They give you
those are for
option.
substituents off of the benzyl?
Those are coming off of the benzene ring. I would argue that we don't want to use the orthoparameta because we've got a nitrogen already there. We're saying that N location, and I think to me that looks messy. There's got to be a better reason than it looks messy, but it's nomenclature and it's somebody arbitrarily decided it, so they might very well have something decided that way.
Just so you know, everywhere in the study guide, any answer that has O, M, or P is automatically wrong.
Interesting.
They do not use it at all.
They don't.
So O, M, and P must be a common name application. That's interesting. I didn't know that.
Every single answer is in its route. Because they'll give the IUPAC with the 4, and then they'll give it with the P.
So IUPAC, use your numbers. IUPAC's got to be numbers. Interesting. Learn something new every day, right? I'd rather not learn about nomenclature, but. Okay, other questions on that? Did I get that one completely right? Okay. It's nomenclature. I hate nomenclature. This is I decided when I took organic that I'm not going to do nomenclature.
It shows the
so-
ridiculousness of the ACS test.
Yeah.
though.
Well, they don't do a full test on nomenclature. So you see a couple questions. You might see one question at kind of this level of difficulty, but most of them are going to be fairly straightforward, shorter compositions. So on the ACS test, when I took it, I would ignore this question. I'd probably name the pieces that I saw, and looking at those answers, I kind of went, oh crap, a lot of those answers looked reasonable. So I probably would have guessed and moved on. Okay? Don't waste your time on things that you feel weak with. Okay? Take your best guess and move on. And don't guess E. Okay. So, other questions? Okay, I know that's a real uplifting, heartwarming slide to start off with. After that, that's kind of our nomenclature behind our amines. That one was kind of a dodge on the amines because we looked at an amide functional group. So make sure that you know your functional groups so that you can name appropriately. Okay? All of those answers were amides. Okay, so you can sometimes get away from some of those issues by naming, just looking at your multiple choice to say, oh, I'm naming it as an amide. It must be an amide. Okay? So your general introduction to amines, it's always kind of fun to show electron density pictures. what we're referring in that picture is that you're seeing a lot of electron density around that nitrogen, which is why it's red. Okay? With a source of electron density, how do you think it can react? So what definition matches electron density? Nucleophiles and bases. Okay? So all of the chemistry that we would see in this chapter is either the amine acting as a base or acting as a nucleophile. 90% of the chemistry, I would argue, within this chapter is stuff you guys have already seen. They're now presenting it and saying, oh, look, it's an amine, now it's magically new. Okay? It's the same stuff that you've seen before. Where amines show up primarily in the the ACS test that I've seen is they'll ask you to rank bases. Okay, why? Because nitrogens are darn good bases. So you need to be comfortable with ranking your acids and bases based on those definitions. Okay, which means you need to know your definitions. If it's going to act as a base, what does it need to do?
Give up the,
So we got two definitions. You said donate, so you want to finish that one for me because you started. Donate.
Donate the hydrogen, accept the hydrogens, and donate electrons.
So we have two definitions. Donate electrons or accept hydrogens. Doesn't matter which way you look at it, they're ultimately doing the same thing. So if I want to rank base strength, the strongest base means those electrons must do what? Leave the structure. Okay? Either going to a hydrogen or towards a nucleophile. Okay? So I have to take those electrons and donate them somewhere. So what's going to make it a weaker base?
It's more electronegative.
So electronegativity can contribute, but we're saying it's nitrogen. So between nitrogen and nitrogen, we can't do anything with electronegativity.
When you look at the electron density being pulled away from
We want to see what those electrons are doing. Are they being pulled into the structure? In which case, they're not free to go out of the structure because they're getting pulled into the structure. Which means necessarily it is going to be a weaker base. Right? How can you draw electrons shifting around, particularly going into a structure? What would we be using? Resonance. Okay? The other thing that you could use would be the inductive effect. If you had a bunch of halogens or something like that, drawing electron density inductively into the structure. Okay? I've seen lots of practice questions where you're seeing a lot of balance between resonance and induction. So make sure you evaluate at each of those stages and find that primary difference. And then decide, do I need to look at resonance? Do I need to look at induction? Slowly, stepwise through it. If you're asked to identify a base, the first thing that you should make sure you identify, electrons. Find the most basic electrons within every single structure. Once you have the electrons identified, then you can start to treat them and see what you can do with them. If you just start randomly picking random pairs of electrons, you're going to start to get confused. So identify your one pair of electrons and use that as your sole provider for electrons and see how those electrons can move within that structure. Okay? So we get it as a base or a nucleophile. When it's acting as a base, we're reacting it with hydrogen. If it's acting as a nucleophile, we're reacting it ultimately with carbon, but it could be with a variety of other things as well. Okay? Typically, we're looking at carbon. This is an interesting concept that you may or may not have heard of when you were talking about stereochemistry. If we take a look at a nitrogen, okay, standard, let me draw out a nicer example of a nitrogen. How many groups of electrons are around a primary nitrogen? Let's make this a hydrogen, this an R group, and make this an R prime.
4.
There are 4 different things around that nitrogen.
Did you say primary?
Around a primary, oh, I see what you're saying. Around this nitrogen.
Okay.
Okay, technically we got this drawn as a secondary nitrogen. Okay, there are 4 distinct groups around it. We've got the hydrogen, our purple R group, our blue R group, and a lone pair. Those are 4 distinctly different things. Okay, if you think back to stereochemistry, what does that mean about the nitrogen? It is chiral, which means we have a stereocenter. Why did you very rarely, if probably ever, look at nitrogen in the stereochemistry chapter? So the general rule is that it has to be carbon. Nitrogen doesn't work even though it is a chiral center. If I take a look at a nitrogen atom, that nitrogen that I've got drawn up there, for instance, that is absolutely chiral. That molecule will rotate light. Why, when I take that molecule and drop it into solution, does it stop rotating light?
So how would you like the lone pair to be?
Okay, which is one of the reasons we can dodge that, because we don't need to worry about that. What happens with that lone pair? If we take a look at the drawing that the textbook provided you, what happened is we move from left to right. Lone pair is on the right-hand side versus the left-hand side. Well, that's not that big of a deal. We can just pick it up and rotate it. Did we pick it up and rotate it, though? No, it's an inversion. How can it invert? Okay, well, remember, those lone pairs are associated with the nitrogen, which means they exist somewhere around the nitrogen, which means they can be on the left-hand side of the structure. They could also be on the right-hand side of the structure. For them to shift to the right-hand side, though, that means all the other groups must push the other direction. So what they're trying to show here is that our lone pair is actually migrating, still have issues with my right and left, from the right to the left side. As it migrates through the nitrogen, those electrons get closer to these groups, or closer through the nitrogen. Those groups start to pop back the other direction. At our complete transition between it, what we've got is effectively a p orbital. Okay? And that's what they're showing up at the top. Then the electron pair can completely push across and we get back to our sp3 tetrahedral intermediate. Nitrogen's lone pairs can kind of oscillate back and forth between the structure. What does that end up doing? Well, if I started with an R chiral center and the nitrogen does its little self-inversion, I end up with the S. So if I'm going to test the optical activity of a nitrogen compound that I think is chiral and I drop it into solution, the thermal energy within any environment is enough to allow the electrons to pass back and forth between the center of the nitrogen. Which means if I start with one that's 100% R, in the course of that thermal energy of it just existing, some of it transgresses into the S. Which means when I now put it into solution to test it, I don't have pure R, I have a mixture of both the R and the S. And since there's nothing in the solution to prefer one or the other, I get an equal mixture. Okay? So why do we not talk about it when we talk about stereochemistry? Well, first off, you should have. Okay? But second off, we don't talk about it very much because if we were going to try and test the optical activity, or even its reactivity in stereoisomer effects, it neutralizes and it becomes a wash, and we get an even mixture of both. In fact, it becomes a racemic mixture around that nitrogen. Well, if it's racemic, we don't really care about it, okay, as far as the nitrogen is concerned. Okay? So that's one of the reasons why you typically won't see that. Be aware that it is still technically a chiral center. Okay? But in the course of the reaction, it can still oscillate, which means in that oscillation process, we lose that chiral center and we don't have to stress as much about it. Yes?
Did we not learn about it too? Because it doesn't really talk about prioritizing the lone pair compared to hydrogen.
We could look at a prioritization of the lone pair as well. And the reason we dodge that question is because that lone pair oscillates back and forth. So if you looked at a carbanion, same thing. You're going to get the exact same result. We can't prioritize it because it doesn't exist in that one spot only. It exists in both spots. Okay, so we can't really set up an RRS system in that case. Okay? What would happen if we, say, froze the sample? That's an interesting idea.
You would have frozen it at the racemic mixture anyway.
Well, that's true. But let's say that we could somehow favor one form or the other, okay, to some extent, and we then froze it at that point, or froze it and then picked out the individual crystals. We should be able to see optical activity, okay, because we've prevented that oscillation. How easy is it, or how cold does it have to be to do that? Probably really, really, really cold. You're trying to prevent pretty close to prevent electron motion. And to do that, you're really, I mean, that's pretty much at absolute zero. It's not exactly that low because it's not just the electrons moving. It's the bonds that also have to move with those atoms. Okay. But theoretically, we could freeze it in that position. Okay, so kind of a neat observation with our nitrogens. They can readily be protonated, so common to see in biological systems in their protonated states. The reason being is that most biological systems have a low enough acidity, high enough acidity, that they actually end up getting protonated. Okay, so you'll see them as the ammonium ion. Commonly found in biochemistry, you'll see that all over the place. Okay, and they'll start talking about pKa's and PI's and all sorts of other junk like that. And I'll leave that for your biochemistry lecture, okay, to go through that detail. You will definitely quantify the crap out of that like you did in 152. Okay? We can quantify it at our level by just saying which side is favored. The weaker acid, which means the larger pKa. Okay, so you can look at an individual reaction given that pKa value and say which side of the reaction is favored. What's that?
Even though you see charges.
Even though you see charges. Yep.
The way I saw it too is the oxygen will more readily take the electrons from the hydrogen than the nitrogen will.
Yeah. So on everything we've talked about this semester, and I've been surprised it hasn't shown up yet, I always say something, we always want to get rid of charges. Always get rid of charges. Works most of the time, not always, okay? Because we do end up generating charges in this case, but these end up being more stable charges. The negative charge there has resonance, whereas if we look at the electrons and then the other side, we don't have any resonance to stabilize the effective negative charge on the other side. Okay. Solubility and reactivity is what this slide is looking at. Nitrogens with a hydrogen can do the ability of hydrogen bonding. So if we have relatively small nonpolar sections on our nitrogens, we would expect high water solubility because we get that hydrogen bonding effect. Okay, which kind of makes sense. How could we increase the solubility? Okay, you probably all did this in lab. Not this semester. Did an extraction lab where you separated a carboxylic acid away from an amine compound. How'd you do that? Laughing, that's always a good sign. Follow the directions in the lab. True, very true. What does the amine act as? So it's reacted with an acid, what happens? If it becomes positive, it is now an ionic compound. What other compounds are ionic?
Salts.
Salts. What's the solubility of salts?
Very, very high.
Almost all salts are water soluble. So we started with a compound that, while it had hydrogen bonding, wasn't all that polar. Okay? So its water solubility is limited. If we add an acid, we can very quickly and reversibly, which is the best part, turn it into an ionic compound. Our ionic compounds are salts. Nearly all salts have massive solubility, okay? Because we get a strong interaction between the ionic compound and water. Okay? So that's how we would take care of extraction techniques. This slide is taking a look at effectively our base strengths. So first question I would actually ask, let's compare, go ahead and star it, our middle structure to cyclohexylamine. Which one would we predict to be more basic? Why is the one I've drawn more basic? Okay, so when we're looking at a base question, we need to identify our lone pairs. And I'm going to draw that so it's not in the black. Where's our lone pair?
On your nitrogen.
We're looking at our nitrogen. So some of you, if you've asked questions about these, I ask you to draw these wicked big. Okay? I want those to stand out and jump at you so you know specifically what you are looking at. If we go through and look at our other ones, same deal. We've now identified our basic position. We want to decide which of those is more basic. Well, for it to be more basic, it must send those electrons towards hydrogen. The electrons must leave the structure. All right, so if it's going to be less basic, what else could we do with those electrons?
Send them into the structure.
Send them into the structure. So a very good first pass when looking at acid and base strength, resonance. Can you draw a resonance structure? When we take a look at this guy, we can put that pair of electrons onto the carbon in the ring. If we go through and try to do, this one's a really big lone pair, geez. Try to do it on this one, what's the problem? How many bonds would this carbon now have? It would have too many bonds. We'd have to break a pi bond. The only pi bond we have got is the one we just made. Goes right back, which means
No resonance.
there is nowhere to put those electrons. The only place those electrons can go is out into the solution. Whereas if we take a look at our red starred one, where could we put those electrons? Into the structure, which means there is another place to put the electrons other than with hydrogen. What does that mean about its base strength?
Weaker base.
It's a weaker base. Okay? If we now pull that kind of same logic with the other structures drawn up here. Okay? So let's compare it now to the methoxy one. Okay, our starred to our methoxy. Both of them have that resonance ability, donating electron density in. Okay, so our first pass is pretty useless. We got to keep pushing. Okay, so what we would try and do is identify the difference between these two structures. Where is that difference? The methoxy. What's special about that methoxy? Yeah, what about the oxygen? We're comparing that oxygen to what atom? The hydrogen. What's the difference between oxygen and hydrogen? We do have an electronegativity issue, but remember with our oxygen, we have the lone pairs, and what can we do with lone pairs? We can donate electron density into the ring. This electron density continues to go around the ring, whoops, and we can put negative charge on that carbon. If I put negative charge on that now purple carbon, can the nitrogen donate electron density in?
No.
That now puts way too much electron density in the same spot. So what does that nitrogen do with its lone pair? Pushes it outside towards the hydrogen. It is physically getting pushed out of the structure. What was getting pushed out of the structure? What does that do to the base strength? Makes it a stronger base. Okay? So look at those effects. I have seen people writing activator versus deactivator. I don't necessarily want to say that's wrong, because it is still technically correct. Our methoxy is an activator. But when do we use activator versus deactivator? EAS reactions. Are we running an EAS reaction? No. So it's not that it's necessarily wrong. It's that, to me, you're starting to cross terms, which is going to increase the likelihood of getting something wrong. Okay, you could still do it right. It's just, it makes me nervous.
Wouldn't, so I think based off electronegativity, if you look at the oxygen and the nitrogen, wouldn't the nitrogen be more willing to put his lone pair into the system and the oxygen?
True, but is that the difference in our structures? So you have to evaluate where our difference is. Our difference is not the nitrogen. The nitrogen is the same in both cases.
I guess I was just looking at the basicity of
So
that atom alone.
if we look at that atom alone and we want to try and evaluate then what's the question that we would ask?
Which part of it is the basic? Or
Okay, so if we go under that assumption, which part of the structure is the most basic? It's still the nitrogen. It doesn't matter that it can donate its electron density in better than the oxygen. The question is just what are we looking at? If it's going to act as a base, nitrogen can do it better than the oxygen, period. Okay? If we're going to compare to our starred structure, okay, they're both nitrogens. They can both equally donate into the structure. Okay? Where the difference is that we're now looking at a hydrogen versus oxygen, and our oxygen can donate electron density into the structure as well. Okay? Much more so than the hydrogen. So it has nothing to do with the nitrogen at that point. It's only oxygen versus hydrogen. Oxygen can do more. Okay? So make sure that you know exactly what you're ranking instead of trying to evaluate all within that one structure. Identify your basic atom, okay, or your basic electrons, and then compare what you're, or make sure you're answering the question, compare it to what you're asked to do. Okay, does that make sense? So you
You're
don't.
saying because the oxygen will donate into the ring more, that makes the nitrogen even more willing
Donate more than what?
than the hydrogen.
Than the hydrogen.
Into the ring.
Yep. Which effectively makes the nitrogen
More willingly.
more willingly put out the electrons out into the solution. Or we could say it's less willing to put them into the ring. Okay, both are valid options. What happens when we look at the last solution? Well, in that case, it can be helpful to draw out a Lewis structure. That carbon becomes relatively positive, electron withdrawing. If the electron density is drawn out, what charge builds on that carbon? A positive. How can I stabilize that positive? I can dump the nitrogen electrons into the structure, which means that last one becomes even less basic than every other structure. Okay? So evaluate at each stage. Okay? What I would recommend for any ranking question is pick 2 structures. The rest of them are irrelevant. Ignore them. Rank those 2. Then pick another 2. Ideally one that you've already looked at because you've spent some time to organize that. And then rank those 2. Now start to compile your information. All right? If you got it then, put your answer down. If you need to rank the last one, do the same idea. Okay? So slowly build your ranking system. Yes?
What about that other nitrogen that has the other lone pairs? Would that contribute anything to the basic?
That nitrogen, good question. Could have Zena answer this one for you.
Which one?
In our very last structure, we have another nitrogen down here with a lone pair. Which nitrogen is more basic?
The one on the right, because when you have different hybridization, it changes the acidity of the atom. So if you compare Sp to Sp3, they call it the S character.
Yeah.
So the
So
more
we could look at a
yeah.
hybridization effect on that as well. Okay. And this, wow, they call these amides. That's awesome. I mean, oh no. Are amides basic? So if we switch that up a little bit, what do we expect of the basicity of amines? Would we expect the lone pair on that nitrogen to be relatively basic?
Well, it has capability of resonance.
It has the capability of resonance, which means it shouldn't be very basic. All right, so we expect very low basicity for our amines. Okay? So our acid-base questions, there's a lot of individual things to process. Go through it stepwise. Okay? Look for charges, look for atom effects, look for resonance, look for induction, and then after that, guess. Okay? You won't get to that point because one of the other places will show up. Okay? Oh, yep.
We're only dealing with pKa's, no pKb's.
You'll only see pKa's. Why do we typically only see pKa's?
We're working with bases. So
As far as I'm concerned, I think it's arbitrary. Okay? Pretty much exclusively everybody works in the pKa system. You very rarely see anybody do a pKb. Okay. Amines would make a little bit more sense to look at a pKb for. We just don't. Okay. Making amines, we've got 3 different methods up here. You've seen all of these. Our very first one, we end up going through and making our nitrile first through a substitution reaction. Once we've got the nitrile, we can reduce that down to a primary amine, so we can get our nitrogen on there. In the second case, very similar situation. We can take a carboxylic acid and convert it into the amide functional group. To do that, we have to get it up to that higher activity first, get it into our acyl chloride, then we can shift into the amide functional group. Okay? Or we could try and do an equilibrium situation, which isn't going to get you high yields. Once we've got the amide, we can again reduce off the carbonyl and be left with our primary amine. I want to say we talked about this very last one, but I'm not positive we did. We can put a nitro onto an aromatic ring, and then we can reduce the nitro functional group into an amine. Okay, there are a few reducing agents you can use. Hydrogen and platinum apparently works, and then you get that big long list of other possibilities. I think the most common one I've seen is the tin chloride and acid. Okay, to put on the to reduce that NO2. Okay. So we do have those other possibilities for getting into amines. The textbook then seems to think that this is now a new synthesis. To me, it doesn't look like a new synthesis. Okay, what type of reaction are we running?
Substitution.
It's just a straight up substitution. We have a nucleophile attacking an electrophile with an leaving group. And all we're doing is a substitution reaction. Okay? The nitrogen being a pretty good nucleophile, we don't need to do a whole lot to it. We can just go through and pump it out. Okay? One of the problems with this is that our leaving group is so good and our nitrogen, our leaving group is good, our electrophile is relatively electrophilic, and more importantly, our nucleophile is such a good nucleophile that it doesn't stop after one substitution. It'll usually continue to do that substitution until it's fully saturated or fully replaced all of its hydrogens with nitrogens. Okay? So that's kind of a problem with that synthesis. What they're talking about there is your quaternary ammonium salt. So what we end up doing, so quaternary means 4. In this case, we're looking at CH3s. Our tertiary would be here, but we still have that lone pair. That lone pair can react a 4th time, and we end up with that structure. Problem with that, nitrogen's now lost electrons, is now positively charged. So we end up forming a salt between the ammonium ion and our iodide. Okay. And that just has to go with how good of a nucleophile our nitrogen is. It really does just kind of push that reaction along. Okay? Other things that we could go through and do if we wanted only a primary nitrogen or a primary amine. We could limit its exposure by, instead of having the nitrogen act as a nucleophile in the amine state, we can go through and react it with a compound known as azide, okay, or sodium azide. We're looking at 3 nitrogens all linked to each other. Whoops, that was the wrong button. Oh, and I'm not sure I can draw the Lewis structure off the top of my head. Oh, maybe I can. I lied. There it is. Look at that. Our sodium azide will act as a nucleophile. Backside attack, kick out our leaving group, and we can get the azide attached. Once the azide is on there, you'll notice that we have a lot of pi bonds within that system. So we could reduce it with hydrogen and platinum. You'll notice the end result is either, we could reduce with hydrogen or platinum or with our lithium aluminum hydride, another hydrogen source, which works well with double bonds. Okay? What happened to the other nitrogens? Because they aren't there. One of the side reactions or side products in this is nitrogen gas. we also release that nitrogen gas, which is one of the driving forces for this reaction. Okay, we can reduce that down really well, and it happens to push to our amine nicely because we can release that nitrogen gas. Okay? So kind of a neat system in that case. This one I think is kind of the more interesting synthesis in my opinion, known as the Gabriel synthesis. And for some reason that always elicits like some crazy angel-looking thing wielding a big sword. I mean, if you blur your eyes, the reaction almost looks like that, right? Really, really blur your eyes. What we're starting with is potassium phthalimide as a nucleophile. So that is the phthalimide structure that they're looking at on the left. That nitrogen ends up being pretty acidic. You'll notice that it is an amide, and we looked at its base strength before, not its acid strength. And even on its own, a standard amide isn't the strongest base, or sorry, strongest acid. Why is this one so much more acidic? What if we change the structure around a little bit and made it look like, say, this guy? That's an eraser. What can you tell me about those hydrogens? They are acidic. We saw that in what chapter? 22, what we were just tested on, looking at carbonyl, that alpha carbon reactivity. What do we effectively have in our phthalimide? Yeah, we have an alpha nitrogen. Would we expect this hydrogen to be even more acidic than our carbon structure? Yeah, why should it be more acidic? What's the difference? I don't like the more electron argument. It's electronegativity. Our difference is nitrogen versus carbon. Which one's more electronegative? Nitrogen. Which one can stabilize the negative charge better? Nitrogen. Our phthalimide should be more acidic than our diketone, okay, for that very reason. So evaluate, start at the top. Look at your charge effect, then atom effect. Our very beginning of this is an atom effect. We're looking at carbon versus nitrogen. We would expect that nitrogen to make it a lot more acidic because it's more electronegative. Okay? Once we've got the potassium phthalimide, we now have an interesting situation. Our nitrogen was nucleophilic to begin with. What did we just do to it? We made it even more nucleophilic. So even though it is now sterically blocked, okay, with all that other junk on it, it is an incredibly good nucleophile that can now attack our leaving group. Okay? The nice part about that is that once it does that standard substitution, okay, we still have that lone pair, but is that lone pair available to act as a nucleophile? For it to act as a nucleophile, it must leave the structure and react with another alkyl group. Okay? Problems with that? It's a sterically hindered nucleophile at this point. So that's going to limit the reactivity. Take it a step further. Is it just sterics that we need to be concerned about? What else can we do with that lone pair?
Resonance.
We can resonance into the ring. So we could start with our phthalimide that had a lone pair, not very nucleophilic because of a steric argument. Remove that hydrogen. Now it's really nucleophilic because of that negative charge. We can then do the attack, and now it can't attack a second time because of sterics and a resonance argument. Okay? So that limits the ability to do that multiple substitutions. So that's kind of nice. But the whole point was to get an amine. Do we have an amine? We have an amide, so we still aren't there yet. Okay? Before we do that, why would we expect the SN2 and not the SN1? Strong nucleophile. What else is going to be a contributing factor? It's steric hindrance on our nucleophile, which is a little bit odd. We typically look at steric hindrance on our electrophile. So we're suggesting SN2 dynamics. What kind of electrophile would we expect to react best?
Primary.
A primary, because primary push SN2 better than secondary or tertiary because of the least steric hindrance. Right? So what we can go through and do is make a good primary amine in this fashion. Well, still not quite yet. So we somehow have to go through in our next step and do what? What do we have to do to make this into a primary amine? We need to break these bonds. Okay, what would we need to break those bonds? Where do those electrons need to go? Should they go with the nitrogen or with the carbon? Should they go this direction or should they go this direction? Why should they go to the nitrogen? Yes, the nitrogen is more electronegative than the carbon, which means our carbon is going to be what charge? Our carbon is likely carrying a positive charge. So to help facilitate the breaking of that bond, what do I need to react this structure with? A nucleophile. What's a good nucleophile? Try and throw in nitrogen, but we're already generating a nitrogen, so that's a bit questionable. We could probably try that, but we could throw in an oxygen. What functional group would we get if we threw in an oxygen?
Carboxylic acid.
Carboxylic acid. What's nice about that? That's a legitimate, stable functional group. Okay? So what we want to throw in is some kind of oxygen nucleophile. The one we're going to choose could be H3O+. So we can add the acid to help facilitate the breaking of that bond, and we get a dicarboxylic acid. You mentioned the nitrogen. My bad. Good job. We could also use a nitrogen nucleophile. In this case, we'll use a dinitrogen nucleophile. Why would we pick one where the nitrogens are attached as opposed to individual? We don't want it to compete with our other nitrogen coming off. The other thing that's nice about having it as a dinitrogen,
Less reactions have to take place.
it's still going to be the same number of reactions, but how swiftly will they occur after the first reaction? It'll go a lot quicker. Once I put the first nitrogen on, where's the second nitrogen to react? It's right next to it. I don't have to wait for a diffusion through the solution. So hydrazine, which is the name of that compound, they will undoubtedly mention hydrazine. I don't think they'll expect you to know that name. Okay? Hydrazine works really well as a nucleophile in this case to help cleave out and kick out our now primary amine. Now that we got our primary amine, we could propagate that into whatever other chemistry we wanted to do. Okay? So kind of a neat reaction, or sequence of reactions rather. I mean, we're running 3 different steps to just make a single functional group. Okay? Which brings up another interesting point, I guess. A lot of chemistry is pushing towards green chemistry. What do you think the Gabriel synthesis ranks as far as green chemistry? Probably at the very bottom of the list. Right? We have to use a whole bunch of other pieces to go through and get that activated to the point to generate our product. Okay? So we've got a huge amount of waste in this experiment. Okay? One of the reasons why the hydrazine could be nice, if I remember this correctly, this compound, our hydrazine product, I think I'm remembering it correctly. If we put this in the presence of a base and oxygen and iron, it fluoresces. Where would we find oxygen and iron? Rust is an option. There's a more important place. Blood. It's how we make luminol. Luminol becomes important. If you've ever seen CSI and they spray that junk all over the place, they're spraying luminol down. What that will do is that compound will react with iron found in blood and decompose into a very excited state structure. That excited state structure needs to release that energy. It releases that energy in the form of fluorescence. So we can see that fluorescence. Oxygen is required to help that reaction go. I think oxygen goes through and we form, I think, the top product, the diacid. Okay. It's an experiment we've done at Mesa. It's a big mess, but kind of entertaining. I thought about doing it this
So what they
semester.
do to like see blood and crime scenes?
Yep, that's exactly what they use is luminol. Okay. So we could kind of sneak out of it and say, oh, it's totally a green synthesis because we're making this compound that now people can find murderers. That's a good thing to do. Okay. So we could also go through and make amines through a process known as reductive amination. I think it's a bit of an odd misnomer because it's really an amination followed by a reduction, not reduction followed by amination. So we could start with a ketone, and we could react that with a nitrogen to form an imine. I should remember that from chapter 20, I think is what that one was. Okay. Once we've got that imine, we have that double bond. Well, what can we do with pi bonds? We can add hydrogen to them. We can reduce them. So we could add our H2 and platinum, and we can now take that down to the amine. One of the things that's nice about this is that we can pick up our secondary amines. Okay? Whereas our Gabriel synthesis really only worked with our primary amines. So kind of a neat system there. If we want to one-pot this, okay, so what do we mean by one pot? Let's tweak this structure a little bit, and instead of it being an R group, I'm now going to add on an alkene. Why not? Let's add a couple alkenes. What happens when I get that H2 and palladium, or platinum? I'm going to reduce the alkenes. Okay, but what if I want those alkenes? Well, this method then sucks. So we need some way to tweak it. So what we can do to tweak it is use a more selective reducing agent. And that's what they're showing in this case. We can use this reagent, which should look kind of familiar. What does that reagent look like? Looks like sodium borohydride, which is effectively what it's doing. That cyanide group, or that nitrile attached to our boron, that extra little piece limits the reactivity so that it reacts a lot more selectively with our amine, and we don't have to worry about it reacting with, I think, even our carbonyls or alkenes. Okay, so we get some better reactivity in those cases. And we can run this with both our primary, secondary, or tertiary amines. Okay, also kind of a nice deal. Okay. Okay, so we're actually pushing now kind of into the home stretch of this. We've got a whole bunch of summary slides effectively here. So really they're showing three main syntheses to go through and make your amines. So you've got your Gabriel synthesis, which I personally think is the coolest. You've got your azide synthesis where you're releasing that nitrogen gas. And then you've got your reductive amination. Okay? At least at ASU, I've definitely seen the reductive amination show up a lot. That seems to be kind of a professor favorite. They are more experienced than me, so if they like it, the ACS test will probably also show some reductive aminations in there. Okay, so kind of be aware of that chemistry, which is a good one to show up because that gets you reduction, and that also gets you that carbonyl chemistry as well. Okay, so it's a little bit fancier chemistry as opposed to the other ones, which are really just kind of straightforward, boring substitutions. Okay? So once you've got that primary amine, you can then do a variety of other things. So your textbook now goes through and says we can do a sequence of reductive aminations with the primary amine, now being our nucleophile. Okay? So in that next step, what we would be doing is reacting our primary amine with a ketone, actually probably an aldehyde in this case. Okay? To form our imine, we would then reduce that, and we now have that extra R group attached to our structure. Okay? You'll notice that they don't show the R group directly attached to the nitrogen. Why not? What is our nitrogen reacting at on our this structure? It's reacting at the carbonyl carbon, which means when we do the reductive amination, it is a carbon plus the R group, which is why when they show each of these reductive amination steps, you'll notice that you see that extra carbon in each of those. That extra carbon is a necessity from the reductive amination.
So the H2 reduces the oxygen or the carbonyl?
the nitrogen comes in, does the or your addition elimination, and we completely swap out the oxygen for the nitrogen. Okay. And then you reduce and get rid of the pi bond between the nitrogen and the carbon. Okay. Interestingly enough, should they have drawn that extra carbon there? That I just circled. I know you guys were all looking down at that exact instant. Was that a necessary carbon to add in there? In each of the Gabriel, azide, and reductive, or the reductive amination one, we would need that carbon. But the azide and the Gabriel synthesis, we'd be directly attached to the R group. Okay? So the reductive amination is the only one that insists that you add that extra carbon, then your R group. Okay? So you might want to be careful when you go through and look at these kind of reactions that you're counting your carbons and not losing them. And I'm sorry, I totally just talked over. Okay? So we will finish